Last topic from this chapter is the concept of impulse, and that is when objects collide with each other during collision, what happens? So during collision, when a baseball bat is hitting the baseball, um, how is the momentum of each one of them changing? Remember, overall, the momentum of the system remains the same, but the ball's momentum gets changed and the bat's momentum gets changed also. For example, if ball is coming the certain velocity and the batter hits with the bat, it changes not only the direction of travel of the ball, but velocity also. So individual particles or individual objects experience change in momentum. That change in momentum is called impulse. Okay. The change in momentum of an individual particle is called impulse. It's usually written as J. Impulse is written as J. Now remember, delta P over delta T is equal to net force. So if I want to calculate delta P from here, that has to be net force multiplied by delta T. But delta P is impulse. So impulse is net force acting on an object for a certain period of time. That period of time is usually called the contact time. How long was the contact between your foot and the soccer ball, right? So that would be considered a collision. Now, if we take human as you and the soccer ball as one system, there is no change in momentum. But if we consider individual objects, like your foot as a separate object and soccer ball as a separate object, each one will experience a change in momentum. So each one will have an impulse. Impulse is just change in momentum, so units are kilogram meters per second. What if the change in momentum is related to, in such a way we write it, because instead of delta P, we use dP over dt. So what if momentum is given as a function of time? In that case, change in momentum is f dt. So then you integrate both sides, and impulse J is going from some initial value to final value, f as a function of time, dt. So that's the definition of impulse in integral form. Okay. It's still change in momentum, but if force is given as a function of time, then use the integration formula instead of using just the delta P formula. The curve is just showing you how momentum impulse is area under the curve of force times time. If you are given force as a function of time, in order to calculate what is the impulse, you will integrate it with respect to time from some initial or final value, which is same as saying it is area under the curve. Let's solve a problem based on that. 0.25 kilogram puck is initially stationary on an ice surface, no friction. At time zero, the horizontal force begins to move the puck. The force is 12 minus 3t square I hat. So it's a function of time. They're asking you to calculate impulse. Whenever there's a change in momentum, that is impulse. So let's write down the given things. Mass is 0.25 kilograms. Force vector quantity as a function of time is 12 minus 3t square I hat. I'll not worry about significant digits now, only in the end. Initial time is 0.5 seconds, and final time is 1.25 seconds. So impulse is then integral from initial time to final time, f of t dt. So that is from 0.5, it's a definite integral, 1.25, 12 minus 3t square dt. But don't forget I hat because it's a vector integral. Okay. What is the integral of the first term? That's going to be 12 t. Limits are 0.5 to 1.25 minus 3 t cube over 3, 0.5 to 1.25, whole thing multiplied by I hat. 3 cancels out. Apply the limits. Impulse is equal to 12, 1.25 minus 0.5 minus 1.25 cube minus 0.5 cube. And then remember, whole thing multiplied by I hat. The answer for impulse comes out to be 7.171875 I hat. Rounding it to 2 significant digits, J is 7.2 kilograms meters per second, and that's I hat. So the momentum gets changed by that factor. Second part is saying what is the change in momentum of the puck between t is equal to 0 and instant at which force is 0. How do we find that instant when force is 0? Well, force is given to you as a function of time, and that is 12 minus 3t squared. When is force 0? When negative 3t squared is negative 12, or when t is equal to 4. Okay? No, I'm sorry, t squared is 4. So when t is equal to 2 seconds, force is equal to 0, which means now they want you to calculate impulse, but the limits of integration had to be 0 to 2. 12 minus 3t squared dt I hat. So that is 12t minus t cube 0 to 2 I hat. So 24 minus t cube 2 cube I hat. So that is 16 kilograms meters per second. That is the new impulse. Okay, so that's all about change in momentum. Collision in 2D is going to be very simple and straightforward. It's basically two one-dimensional collisions. All we expect that if you know how to do one-dimensional collision, then a 2D collision is going to be two one-dimensional collisions. Just treat X and Y separately. That brings us to the end of the chapter. We talked about a couple of different things, how to find center of mass, definition of linear momentum. We talked about the law of conservation of momentum. We also discussed different types of collisions, elastic, inelastic, and completely inelastic. And last but not the least was impulse, the J that we defined. Okay, so that brings us to the end of the chapter.